Before we get started, we just want to ask everyone to please silence your cell phones. And we also want to thank the guys back at Bungie, all of them who helped put this together. So my name's Joe Spataro. I'm a senior designer at Bungie. On Reach, I was a technical designer in animation. That was a new role, and what I was primarily responsible for was tying together all of the animations in the game engine.
My name is Armstrong. I'm an engineer at Bungie, and on Reach, I was one of the programmers responsible for implementing the features we're going to talk about today.
Let's take a look at some of the animation from Halo Reach.
So we're breaking our talk into 3 sections. First, we're going to talk about our goals for animation on Halo Reach. We're going to talk about solutions to those goals, both with process and technology. And then finally, we're going to talk about the future. First, the goals.
So one of the first goals we had was to ship on time. I think this is a goal that pretty much every game has. And it's pretty obvious, but we adhere to some specific processes and we developed technologies to help make this easier. We had another goal, which was to improve character performances, not just an improvement to animation quality. And the reason that we did that is because we had a host of new Spartan characters, AI characters, that were supposed to fight alongside the player, and we wanted them to have believable personalities and motivations as we told their story. Another goal that we had was to move away from the rigid structure in our approach to content creation. And we want to develop a sandbox of animation features that could serve as building blocks.
So one of the things that makes these goals interesting is the context in which we implemented them. We had some self-imposed rules that were very important. The first is we require rapid iteration. We're going to talk about that more later. The second is zero downtime. The third is through the entire course of development, we maintained backwards compatibility with the old systems from our previous titles.
Part of rapid iteration means that an animator's time is best spent animating. Anything else is time lost. Watching a loading bar isn't a good use of their time. So we developed a one-button exporter that they could export their content, import it, and preview it in the game without having to wait for very long. We also felt that any time that they would spend configuring the game data wasn't a good use of their time either. So we hired a role, which is a role that I performed, just so that animators don't have to spend their time configuring game data. They can just focus on working in Maya and crafting those character performances. Let's talk about the rate of iteration that they dealt with on Reach. They would start off by working in Maya, and they would export a file, and it would go to an intermediate format on the PC. Then they would have to import it, and then they'd have to xsync it to sync it over to their Xbox so they can preview it in the game while it's running. This is a standard pipeline that everyone has. But when we started, this process took a few minutes. And if animators have to do that, I don't know, anywhere from 10 to 50 times a day, it becomes a huge time sink. So throughout production, we constantly kept trying to shorten this time. By the end, we got it down to about 20 seconds.
When I say zero downtime, it means engineering does not let content crash the game. That isn't to say that crashes never happen because of content. But if a content creator can create a piece of content, load it, and cause an assert or hard game lock, that's a number one bug for engineers to fix, top priority. That was always more important than doing anything else. Because of this policy, generally speaking, the animators could work on the game error-free most of the time. We added new systems alongside old systems. This means that we don't take any systems down while we're developing. If we're going to add a new IK solver, which we have in this talk, or a new system for blending locomotion animations, the old systems have to keep working. Not only is this good so that some of the animators who are not working on the new systems continue to operate on the old ones, but legacy content continues to function.
Yeah, we actually shipped with 2 working pipelines, the old one and the new one.
Systems never go down for maintenance. There's no waiting while a new system is under development. We throw a switch, and then it's online, and it stays online after that. We weren't perfect about this in every case, but this was always the rule, and I would say that there was never a time more than a day where an animator wasn't able to work on what they were trying to work on. The legacy systems always working is something I mentioned before. Like I said, we had multiple IK systems, multiple systems for doing jumps, locomotion, even the full import and export pipelines were parallel. All these systems run in parallel or at least can be switched back and forth between. The end result of a character's motion is actually a very complex combination of many layers of IK blends, overlays, other procedural effects. Having the system operate this way makes it nice for switching off individual components to help debug where problems are arising. And also, if something does go wrong with a new system, frequently they can simply revert to the old one and continue working on something else. Because we were making a sequel, old content and characters always worked. There was never a point in development where we said, Master Chief isn't allowed to work anymore, or the old grunt isn't allowed to work anymore. This is particularly important for designers, because in the early stages of development, while new characters are coming online with potentially thousands of animations, designers need something to prototype with and get work done. So these were our goals and the rules that we tried to follow to meet them. So we're going to talk about the process for our solutions to these goals and the technology we used. First, the process.
Prior to Halo Reach, the animators worked without any structure. And by structure, I mean a management or leadership structure. And they didn't really have time to focus on character performance. They really just had time to focus on shipping the game. In fact, they would work on content and not return to it to do a polish pass. They would only return to touch that content if there was a bug to fix. And engineering was always busy and randomized by requests coming from the animators directly or from mission designers. And there wasn't a group of producers that would mitigate that.
So,
and because of that, engineering also wasn't able to focus on polishing. They were just focusing on shipping.
The key thing to point out here, which we'll address on the next slide, is that there was no structure. It was basically the Wild West of animation development.
On Reach, we changed this. During Halo 3, at the height of production, we had 8 animators, including contractors. And we had about half of one engineer's time. The engineer that was working on animation also developed the effects system, so he was splitting his time between both of those. And that was part of the reason why he was busy or randomized a lot. On Reach, because of the size and scope of our content, the new stuff we were developing, we doubled that team size. We had 16 animators. So we needed a structure. And what we did was we had a lead animator that was responsible for maintaining the style and the vision and also the quality bar. But we also elected senior staff as character owners. So one animator who's a senior guy might own the Spartan, another guy might own the Elite, another guy might own the Marine. And they were responsible for making sure that all of the other animators that were doing animations for that character matched and were consistent. We more than doubled the engineering efforts on animation. We had the full time of 2 engineers. And we added a special role, which was the technical designer in animation. I'm going to talk about that in a little bit. We also added a full-time dedicated producer. This was key. The producer constantly shifted the animators onto different tasks when animation features were in development. So if 6 of those animators are working on turning animations, and then the turning system is changing and we need to change the way the content is authored, the producer will immediately shift them over to another task like some other locomotion task so that there's no downtime for them. We also added a full-time animation manager, and the animation manager is like the advocate for the animators. She fought for their needs, and we're going to talk about that as well.
So the manager and the producer function as a dynamic duo. The manager insulated the animators from external pressure. Prior to Reach, animators would have to field requests from engineering, design, and other disciplines, essentially randomly. On Reach, the manager was the filter for all of this information so that the animators could sit in their animation pod and continue to animate uninterrupted. The animation manager fights for the needs of the animation team. We're all familiar with the fact that for any given project, there's 20 features we want to do, and 3 of them we have time to make. So the animation manager was the single voice through which these features were prioritized, spoken for and on the behalf of the animation team. The producer worked with the manager directly at all times. The producer maintained an objective view on the time remaining and the features. This means the producer does not assign a value to what the features are. They do not have input on that. What they do is they set the time estimates with the help of the manager, and then they shuffle things around to make a realistic schedule that's sane, acknowledging that there will need to be cuts. The producer also facilitates communication across all disciplines. There's a lot of meetings that need to happen between animators and engineers and designers to get everything done. The producer arranges the meetings that need to happen, but just as importantly, the producer also tries to make sure meetings that don't need to happen don't. Because we're better off spending time developing than we are sitting in a circle and talking.
So the role that I performed was new at Bungie. It's called Technical Designer in Animation, and I think in order to explain what it is, I first have to explain what it isn't. It's not a rigger. I didn't spend much time working in Maya except to check out the content that the animators had made. And it's not a level scripter or even really a character scripter. I didn't do any of that. What it is a service role. And what that means is that I was always available to help the animators or the engineers if they needed it, or the designers. And that makes it a little bit hard to schedule. But I think that's an important point, is that if you're going to have someone like this on your team, that they need to be available all the time to help out. I sat between the animators and the engineers in the game, so I mostly dealt with all the game data that you would need to configure to make the animations blend nicely together and look good in the game. And I helped the animators by unblocking them, because all of the animations have some requirements, technical requirements, and they may not know what needs to be done in a given piece of content, so I would always help them. And particularly, they would come to me and say, hey, I made this thing and it didn't work in the game. And I would go to their desk and figure out why. I also protected the engineers from the requests of the animators. Because on previous games, the animators could just go to the engineer and say, hey, I got this cool idea for a feature, and the engineer would put it on his backlog. Or they would say, hey, I'm blocked and I need your help. But now they would come to me for that. I worked very closely with the lead animator. The lead animator and I worked closely to develop those technical requirements. And as a member of the design team, one key element of the job was that The animations have gameplay requirements. Maybe a melee animation only needs to be 10 frames long, and the animator wants to make it 100 because that's what looks great. But I had to enforce those gameplay requirements. I also helped out engineers by prototyping, by providing them content. So if Tam was working on a feature like the locomotion or the turns or maybe some of the pose blends that we're going to talk about, I could cook up a file really quickly, and he doesn't have to go through that management structure to get the content from the animators. So he doesn't have to interrupt them and take them offline. There were times where I also helped prototype by even writing native code or tools. So it's important that this role is a generalist.
All right. Now we're going to talk about our technology solutions. First, I'm going to summarize the technology we're going to talk about. Our system for blending movement animations together. Our system for fixing up the feet in response to the terrain and other game events. How we improved our IK systems over previous titles. How we implemented our particularly data-driven pose blend system, the system that we use to achieve aiming and looking, is probably based on techniques that all of you are familiar with, but we tried to do some special things with data driving so that the animators didn't need to be interrupted by configuring game data, as we mentioned before. They could just iterate on files and see it. Ranged actions is actually our parameterized blend of full animations. To give you an example, if you want to jump different distances, how do you make that look good? And finally, the system we use to synchronize animations across multiple characters and scenery objects. One system was used to achieve our assassinations, which we'll show a video of, and our in-game story moments. So, the locomotion prior to Halo Reach was a classic blend of two samples, a walk animation and a run animation. If the yellow dot represents the blend between the two samples, where moving right on the screen it has increasing velocity, we can see that at this speed we're blending a full walk, at this speed we're blending a full run, and then anywhere in between there is some combination. On Halo 3, this is what it looked like. If you pay attention to the video and watch the feet in particular, you'll see the way they float a little bit and don't make solid contact with the ground. That was a very important directive for us to achieve this time, was to try and make the characters feel grounded. Well, the reason that doesn't look very good is the fact of the matter is walk and runs don't blend very well. The walk playing by itself looks great. The run looks great. Anywhere in between, it looks kind of muddy. Why is this? Well, if you take a walk animation and a run animation, scale them to the same length because you're going to blend them together, you can see there's some frames in here that simply don't produce a good result. The properties of a walk, as far as the feet touching the ground go, are distinctly different from a run. In these red boxes, you can see that the walk animation is going to have both feet on the ground, while the run animation may have neither foot on the ground. So what do you do if you blend the foot positions between those two animations? You get some sort of indistinct motion that doesn't read very well. To try and solve this, we wanted to isolate the bad blends first. If we added a sample called jog, which is more like a run, then anywhere between those two speeds, things look great. However, if you slow down, you still have a bad blend. It's just for a smaller threshold of velocity. Finally, we decided to actually separate our movement animations into gates. Walk and fast walk have the same properties of contact, overlapping, and jog and run have the same properties of a flight phase, where both feet are off the ground. Then, as we're increasing from a walk to a run over time, the results will be something like this, where we blend up to a fast walk, then we crossfade to the run. This is very important because this crossfade is a fixed duration, which means even though we're blending animations that don't go together very well, we're doing it for a very brief amount of time. Furthermore, you can decide when to do this crossfade so that you can blend it during the least offensive part of the animation. And then you continue up to a run. This video actually illustrates exactly what I had on the previous slide, where the Spartan starts at a walk, breaks into a jogging gait, and then eventually makes it up to a full sprint and back, with the feet looking a lot more solid. Here's another character who has extremely distinct walking animations and running animations using the same system. It's important to note that this was all data-driven in the sense that the number of gaits that were specified was up to the animator. The number of samples in any given gait was up to the animator. So we're not proposing this and then suggesting that everybody needs to make 5 move cycles per direction. For characters that need to look good during locomotion, you can make as many as you want. For characters where you really don't care, you can actually fall back to the Halo 3 style blends.
Just like the locomotion, the turns that we had needed improvement. One of the issues that we had was that the turn samples from the previous games were very short, and there was only one. So with only one sample, it's hard to get a good range of speeds. And those samples were constantly interpolating at the loop boundary, which kind of muddied the animation. Furthermore, players could change the look sensitivity in the game, and at low sensitivities, the maximum turn rate was actually lower than it was at the higher sensitivities. And what that means is it's hard to make an animation sample that looks good for all cases. So here, if you look, you'll see that there is an animation being played, but the interpolation is kind of muting it. And the animation sample isn't continuous. Even if you looked at it in Maya, it's not playing continuously. It actually accelerates and then slows down, so there's kind of this pause at each loop boundary. The new turning system that we developed used the exact same gate system that Tam just described. The animators could provide as many samples as they wanted, so they could make slow turns and medium turns and really fast turns. The parameter of blending for the locomotion was linear velocity. On the turns, it was angular velocity. So as the angular velocity increased, we moved through those gates. What helped as well on Reach is that we capped our turning rate at 360 degrees per second. If you used a low look sensitivity, you'd still get to 360 degrees per second. It would just take a little bit longer. And once you do that, that means that you can author an animation sample that matches that speed and try to eliminate foot sliding. So we know that this doesn't look really awesome because it's hard to make content of a guy that's turning 360 degrees in 1 second and looks natural. But it's what we did, and we think it looks a little bit better. For the AI characters, we weren't constrained to having the character turn around a single point, so we could actually have them walk around a little bit more and look a little bit more natural. But this too, it used the exact same system.
So fixing up the feet so they respond to the environment. Previous to Reach, foot fitting was pretty simple. The feet are pulled to the ground plane when they're near it. At rest, the pelvis is pulled down to allow the feet to touch. And there was some procedural lean built into the character when they were on slopes. When you watch this video, pay attention to the heels of the character while they're going uphill and how they pull in air. Then after the character turns around, the toes will overhang space. Only when the character comes to rest at the end of the video will he settle into a natural, grounded-looking pose. Looking grounded was, as I said before, a very important thing for us, so we had to do something about this. So we had some ideas. Foot fitting really ought to work in any context or state. We don't want to bind it to any particular type of content. If you're idling, if you're turning, if you're moving, we want the foot fitting to work all the time. We want to actually continuously alter the foot travel path. What I mean by this is we don't want to have a system where we're trying to manage lock and unlock states for the feet with the possible bugs that can introduce and the interpolation in and out of the IK that can introduce. We just want to modify the feet all the time so they're doing the right thing. So there's some things we know about the content that we're trying to achieve these ideas. First, feet travel over a flat ground plane in content, generally speaking. The feet in the content are following a single path that's pretty well determined by the content. The reality is that the world is not a flat ground plane ever, and that the character does never actually move in a straight line. So what we needed was a way to warp the feet so that they would look like they were doing the right thing in real time. If you look at this loop cycle from an actual shipping animation in Halo Reach, we've traced out the path the foot takes. So what I'm trying to say with the foot fitting is that if you bend this path, you can fit the path against the terrain and into the turns the characters are making. You don't have to mess with the whole animation. If you bend the foot path and then IK the feet continuously to that path, you can fit it up slopes, and furthermore, you can fit it into the turns you're making. So watch the Spartan as he goes over the edge and walks down the hill. The feet remain relatively stable and feel very grounded. As the Spartan begins to turn, you'll notice the feet actually turn into the arc the character's making while fitting against the slope. The Spartan always looks connected. A related system, because I mentioned IK, is our improvements to IK on Halo Reach. Prior to Halo Reach, the IK was very static. What I mean by that is the goal that the IK was trying to reach was a fixed point on an object. That's it. You have an FK animation moving around, and then you have an IK point that's fixed. So all you can get is a blend between those two. Interpolation of the end bone on the IK chain was linear. Nobody got to author a curve. They could pick a time that it would take, and that's what you get to deal with. The timing was actually fixed across states, so it was extremely inflexible. The end result of all this is a classic pulling behavior, where the FK animation is moving along smoothly, and then as the IK starts to turn on, the hand or whatever else you're IKing sucks up to the target in a way that does not look natural, has bad performance. And one of the key things we mentioned in our goals is we want to maintain at all times the performance of the animations. So if you look here, watch as the left hand returns to the weapon for these various animations. How it kind of snaps into place at the end like it's on a magnet.
And since the timing was fixed, if the distance that the IK had to travel was really far, it would happen really quickly. And it didn't really look natural.
Same can be seen on melee animations, on weapon switches. So we wanted to prevent this pulling as much as possible and give the animators more control. The IK goal and reach is actually animated in the space of the object. What that means is we have two animations running at all times. The FK animation on the hand and also the IK animation moving relative to the object. If you imagine a hand sliding a clip into a weapon in the neutral pose, the FK is driving the hand with the clip into the weapon at the same place the IK animation is. However, if you use an overlay to move the weapon out of place, the FK animation is continuing to drive the clip into the wrong spot, but the IK animation is now doing it the right thing in its place. Coupled with the ability for the animators to animate the weight of the IK, animate the blend between the FK and the IK, they could opt to switch over to the IK animation at any point. In fact, they would often opt to switch over prematurely. They would blend to IK earlier instead of at the end of the animation, so that if the gun had moved pointed straight up and the reload was playing, the clip would end up sliding directly into the gun because it was being driven by the IK that was animated. This helps reduce the pulling greatly. You can see it looks a lot more natural when the hands return to the weapon. Furthermore, because they could animate the IK weight, the hand is going back to the belt during the reloads correctly every time because the IK is off and FK is driving it. And then the hand returns to the clip correctly. In this example, we're actually showing two different weapons that use the same idle pose, But you notice the left hand isn't in the same place on those guns. That's because our IK could drive it back into the correct place on each different weapon and leave it there.
We're going to talk about pose blends. First, I want to explain a little bit about what pose blends are. You've got a base animation, and you've got a series of static poses that modify that. Like, for example, when you're aiming or looking around, and you want to overlay those on top of the base animation to get a new pose. Prior to Halo Reach, all of the parameters that you could use to use pose blends were hard-coded. And you really only had three choices. You could do looking, aiming, or acceleration. And the way that animators specified which one they wanted was they named their file a special way. They also had to author their content in a very specific pattern. It was something like, hey, the first frame is always the upper left corner, and then you can have one more in the middle and one more on the right, and then you do it for both yaw and pitch. We wanted to move away from that rigid structure and let animators author any arbitrary collection of poses and in any order. The pose also didn't determine the parameter value, and what I mean by that is that when the animators made a pose, it wasn't connected to the values in the game engine in any way specifically. Like, if the animator aims the gun over here, outside in game data is where they would specify, hey, frame 6 is, the guy aiming over here. It wasn't the pose itself that knows that.
And important part about that is that if they got one of the poses in the wrong place, in the wrong frame in the content, they could put an up pose in the slot that was supposed to be the left pose, and then it would just break.
And one problem with this is that it's really difficult to get a character to move around the frame of the Warthog without clipping through it.
Reason being is you don't have a lot of detail when you're confined to a rigid structure like that and you'd like to add more samples around the frame, you just can't without making the entire blend selection more dense.
So our approach to fixing these issues was to data drive everything. We wanted animators to specify not only the poses, but we wanted those poses to sort of have knowledge about what they were trying to do. We let them specify the blend parameters in the editor. So they would make any collection of poses they wanted, and then in the editor they could say, this one belongs to the aim or this one belongs to the look. They could do it after the fact. But we didn't want them to have to do that either, so that's mainly what I did, was a lot of that. And the Spartan alone had like 547 different pose blends. So part of what we needed to do was also to automate that process. The animators are free to choose any collection of poses they want. I think they had a maximum of like 32, and we never went over that. Each pose knows its own value. I don't know if I explained that very well, but there was a node in the file itself that you would align and say, hey, this is the aim direction. And so if you're making something for aiming a gun, you'd want to make sure that the vector that extends from the gun barrel is actually parallel to that node that you're animating.
Well, what's nice about our implementation of that is that the node driving the data was a rig control.
Yeah.
And so you could do anything you can do with normal rig controls in Maya. You could constrain it to the direction of the gun barrel, and then you would just have your content import correctly.
Right. So here's an example of the Spartan sitting in a Warthog, and he's aiming all the way to the right.
Where the green grid represents the different samples triangulated.
Yeah. And here's a sample of him aiming a little bit more to the left. And now one where he's aiming straight up. So we take all three of those poses and we're going to blend them together. But how? If the Spartan aims somewhere in the middle of any of those three poses, we use each of the three poses to generate a weight for each one. We blend them all together, and then we add that on top of the base animation. So if he aims further towards the top, then it's going to be more of that pose. And somewhere in the middle, it's going to be a little bit of a blend of all three. It looks like this. So here, we've added a lot more samples around the frame of the Warthog, which lets him aim around that frame without passing the gun through it. Since the system was data-driven, we could apply these poses to anything. We could apply it to vehicles, we could apply it to characters. So most everything in the game that you see kind of moving around was using pose blends. Here the Spartan is jetpacking around, and we have about 3 or 4 of these things going on. You've got one where we're tilting the body around based on the input of the left stick. You've got another one where he's using the aiming that we were talking about to aim the gun up and down, and also one for his head to look. And there's also one that's a single pose that raises and lowers the thrusters on the backpack. And we were able to add all that stuff without having to ask programmers for anything once they had developed the data-driven system.
It's important also to note that we had different representations of the spaces that the poses were blending in. On the back of the jetpack, it was one line of poses with one parameter. For the aiming and looking, it's actually 2 dimensions of poses. And for things like acceleration, we'd build a sphere of points that we would use to blend vectors, input parameters from every direction. You can see that happening on the Spartan, how he leans into the acceleration. What you might not know about this is we're actually driving the same thing on the chassis of the Mongoose. We have some very strict gameplay requirements for how our vehicles feel and respond physically, but those don't always produce very good-looking motion in the chassis. So using these overlays and driving them by the acceleration on the vehicle, we can get the vehicle to tilt all over the place without impacting the gameplay physics at all.
We developed another system that utilized that triangulated space that we just talked about, but not just to blend poses, but to blend full animations together. Prior to Reach, we used, when we created characters' jumps, we only used a single animation for those jumps. And that jump was parameterized by one value, which was just the jump height. So as the jump reached its apex, you'd be somewhere near the middle of the animation, and as you landed, it would play out towards the end. And when you do that, it really looks good if you're just jumping straight up and down. But once the character has forward momentum, since you don't have anything to represent that in the forward axis, you just have one dimension, it's hard to make it look like the character has momentum. So here you can see as the Marines jump, they're just playing a single animation, and it kind of stretches the character out and contracts him as he lands. So we developed something that we called ranged actions. It selects and blends clips by 2 parameters, the distance and the height, and in the same way that we showed with the pose blends. And something that's key here when we were working on the jumps for Reach was that those clips were aligned in time to key points. Particularly, it's when the character is about to take off for a jump and when a character is about to land. And what this also let us do is to split out an anticipation animation and a recovery animation to make it look like the character is sort of getting ready to jump and recovering from the force of landing. So if you wanted a character to jump in a lot of different distances and heights, you might start by making something like a short jump forward. And then if you said, I want this character to jump a little bit farther, then you might, make a jump where he's jumping really long. And here you can see that there's a red crosshair. That red crosshair represents the ballistic arc that we actually use in the game. We had a tool that let the animators visualize that so that they could animate their characters along that arc and expect to see similar results in the game. Once you need a character that needs to jump up, well, now you have both parameters, both distance and height. And those 3 animations are going to make a triangle. So what we really ended up with was a space of the character jumping in all sorts of directions, distances and heights. And this came from the designers. The designers would say, hey, this character needs to jump really far and really high so he can get on the roof of these buildings. And that would inform us as to how far we should make them or how high they should go. The arrows represent the distance and the height, and that was what you saw with that red crosshair moving. And those distances and heights make, with all the samples, the sample space that we're going to use to blend between. So if the character needs to jump somewhere in between short, long, and high, then it's going to be a blend of those three animations. And also the anticipation section and the recovery section, we blended those together as well.
And just like our other systems, this is all opt-in.
Right.
This character has a large number of samples because the performance of his jumps were particularly important for his gameplay. But for characters that didn't jump or didn't jump very much, you could just author 1 or 2 or 3 samples if that's all you needed.
And also, since it was purely data-driven, you could make a completely different style of animation that used distance and height. Like you could make maybe a character who throws a grenade, and when he throws it really high, he throws it like this, and when he throws it really short, he throws it underhand.
They're headed into the basement. They're headed into the basement.
Is this you?
Yeah. How we synchronized animations. Next piece of technology. First, we want to describe what exactly we're talking about here. We want to synchronize animations across characters. We want to synchronize them with the environment. And we want it to work with any number of participants. If there are 2 Spartans interviewing a civilian next to a crate who's part of the animation, all of those objects are in the synced animation. We use this for our assassinations and our in-game story moments. This system was completely new to Reach. We don't have an analog to compare it with from prior games, but we can point out some of the challenges that we had. Aligning sync actions in the sandbox, which is to say live during gameplay, is very difficult. One of the principles we came up with is that if you have an abrupt or violent start, you can mask the interpolation of the characters into position pretty effectively. This was employed in the assassination animations where a character would dash in, strike the victim, and during that chaos we could line everything up, and then the resulting animations would play in sync after that. For the story moments, we learned very clearly that reaching a good starting point in a good pose specifically is difficult. You need to know things like the foot contact and the transition length, and this needs to be informing your pathfinding system so that you can arrive in the right place at the right time and start your animations. The environment is actually changing during development. You make one of these story moments, and then an environment artist puts a boulder in the middle of your interrogation scene. So the pipeline needs to support a pretty easy update, where ideally you can grab the section of level geometry, bring it right into your animation package, fix up the animation, and then put it right back in the game.
May God help us all.
Here's some assassinations.
Ticket, like milestones, that sort of force.
There was actually a range of assassination samples behind every character. Your angle of entry determined which piece of content would play so that we could have the least amount of interpolation and fix-up possible.
Like this thing.
First strike. Game.
You want to talk about story modes?
We used the same exact system.
Let's go, 6.
To create these in-game story moments.
All right, noble team.
The data setup was exactly the same for assassinations. I could make a file that had all these Spartans and the Falcons in one scene and hand off to an animator. You can just work on it and
clear
iterate.
from this angle.
So here, this is a sync action between this debris pile and these 2 Spartans.
Found the beacon.
Make out any ID?
Negative, but it's military.
So now we're going to talk about the future of our animation technology and process. we have a lot of room left for improvement. We had very rough gameplay to script and back. Despite what I was talking about before, where we tried to take into account the length of transitions and foot placement, we had a lot of difficulty getting characters into place looking natural and difficulty getting them back into gameplay looking natural. There wasn't a good way for the end of the story moment system to say, hey, start this with your weapon down, and then have the gameplay respect that until it wasn't necessary anymore. We also had a complex selection of states and transitions. Basic locomotion was a fairly hard-coded system of selecting move forward, back, left, right, plus all the transitions with all the different weapons possible, and it was not scalable at all.
We didn't do the best job of reusing content. For example, we have both the Spartans and the Marines who pretty much have to do every game action. They have to ride in every vehicle seat and hold every weapon. And they're both bipeds, so their skeletons are relatively similar, but maybe with slightly different proportions. But we actually couldn't share animations between those two different proportioned skeletons. We made animations for both the Spartan and the Marine. It's also difficult to manage the very many layers that we had of content. You know, you've got base animations, you've got all those poses blending together, you've got animations that are replacing some bones to do things like reloads and so on. It's just we had a difficult time managing it.
In addition to that, the IK and other procedural effects were specified in a completely different place from all of those layers, so the sum total of the interactions was complex. Luckily, the future is happening now, and we're working to solve these problems. First, with procedural clip selection. That brittle movement selection, transition selection code, we are trying to get rid of that. We're working on parameterizing all of the animations so that we can develop a system that builds a graph connecting the animations together, respecting momentum of the character, respecting what blends will look good, and respecting settings on how far we're allowed to warp the content to achieve that goal.
We're also working on a motion retargeting system so that problem of the Marine and Spartan will be solved. You can author a set of animations, maybe just for the Spartan or the Marine, and share them across skeletons that are morphologically dissimilar.
An important point to make regarding what Joe just said is that if you're going to start sharing animations, obviously the performance on the two characters is going to be too similar in some cases. So we want to add a way to stylize the animations cheaply and efficiently on the characters that are sharing content. And furthermore, we want to be able to drive these stylizations based on variables coming out of the game. If the thread through this whole talk has been about data driving things and letting the animators work hands off from the engineers, this is just another arena where we want to achieve that.
We're also going to focus on developing powerful new tools that let animators iterate in context. Early on, I showed a slide of the pipeline of how a file goes from Maya into the game engine, and that was the mainline case. When characters are running around navigating and turning and jumping in vehicles, that was solved. Animators hit a button, they could see it in the game. But there were many cases, like the jumps, for example, where it's not easy to get the context to see those jumps play out in the way that you might think they will. So the way that we did it is we made test cases for all those scenarios. I would set up a level where the character jumped all the possible distances and heights and say, here, animator, you can look at your motions in here. In the future, we want to develop tools to make iterating in those contexts much easier.
All right. We want to thank the whole animation team at Bungie that put so much hard work into the game. We want to thank them for providing us the opportunity to give this talk.
We're hiring.
And we'll take some questions.
Hi. How'd you guys deal with first-person, third-person issues, trying to make things look good first-person and also third-person?
We actually use the same overlay system for both, but we use different content. We don't actually run the same animations on the third-person skeleton as we do in the first. We accepted some design limitations to achieve this. Specifically, the first-person animation system in Reach does not interact with the environment in any way. That's something that we're changing in the future, but it kept it pretty easy.
Also, we made sure to maintain the same timings. So all the actions in third person have the same timing as they do in first person. And only one animation owns the events that get triggered. So if a guy's going to melee, then only the first person will have the event in there.
Thanks.
So just related to the AI, what data did you guys take from the navigation system and pull into the locomotion system? So like maybe you take the path or the steering velocity.
It's a great question. Yeah, actually, it sort of went the other way. Some of the animation system data, like the length of the transitions and the speeds, would actually feed backwards to help us generate a better path. That didn't work as well as we wanted it to. So that procedural clip selection system I was talking about is actually going to fully inform a motion model that the AI's pathfinding uses, so that ideally the path that gets generated won't be far off ever from the capabilities of the character's animation. In Reach, because there was just that one connection there of saying how long a transition was, but there wasn't a lot of context, we'd often get cases early on, we fixed them, cases where characters would go from a run to an idle and their transition would take them right off of a cliff or into a grenade or something.
Hi, I'm wondering about your future direction, which is the procedural graph generation approach. I was wondering whether that was a runtime graph generation, or were you doing it offline, like out of the data you gather from Maya?
The graph generation itself is offline, out of the data from Maya, and then runtime, we're navigating the graph.
Great training as well.
Yeah.
When you guys restructured your animation team, did you find that there was a little bit of a game of telephone going on? And if so, what did you do to help that out?
It was still small enough where that wasn't a huge issue. I think if it was bigger, you might get that. Okay. But with the manager and then the lead animator and how we had those character owners, we had kind of like a little miniature hierarchy. It wasn't something that was like enforced or anything, but with that small structure and with that hierarchy, we didn't have that miscommunication problem.
Thank you.
A quick question about when you had to get this game in a shippable frame rate possible state. How much work was there in LODing all these layers of systems and getting it to work and deciding if a character is far away, dropping which systems? I guess you already said that you didn't do a lot of sharing, so I guess the data, I'm sure, was pretty high. But as far as just LODing for CPU performance, was that a pretty tricky thing? Was that also data-driven?
We actually didn't do a lot of LODing for a specific reason. Our game is deterministic for networking purposes. So anything that's connected to the position of the gun where the bullets emerge from or anything like that had to be running all the time. We couldn't degrade it based on how far away it was from a character. So the only things we could actually LOD in the animation system at this time were the render-only leaf bones. If there was a character that had hair or fingers that didn't impact gameplay, or face, we could switch that stuff off. But other than that, all the IK, all the blends, everything was running all the time on all the characters.
And for context, the full res characters had something like 120 bones, and the imposter system would switch to a model that had about 11 bones.
But the full animation had to be run,
right,
and then that animation would get mapped onto the impostered character with fewer bones. So we were paying full price for the animation system constantly.
Did you have to limit the total number of characters, or did the imposter threshold change? Or something?
It was like 40, 50 characters.
Yeah.
Repeat the question. He asked if we had a limit on the total number of characters.
Yeah.
We had between 30 and 40 running, depending on what was going on.
100.
David Aldridge is laughing at me. All right, any other questions?
Yeah, you're talking about as far as reusing retarding animations and rates with these portals. Are you talking about straight retarding, or are you talking about somehow deciding?
All right, I'll repeat the question. He's asked about retargeting and whether we're going to do straight retargeting for characters with different proportions? Are we going to massage the data? What we're actually going to do is, and it's in progress right now, working in a prototype state already, is we have a very lightweight runtime rig, essentially. Same way that in Maya, frequently people animate on a set of controls, where that moving that one control actually derives multiple bones. We're going to be animating our characters in the game the same way, and therefore, if we have a unified rig shared across multiple characters, we can just take the rig animation and move it from one character to another, and it will maintain things like the foot contacts with the ground and the hand contacts with itself and the weapons. Side benefit is it actually makes the content a lot smaller because there's fewer animation streams that we need to save out.
So you showed a pretty nice system between walk and fast walk and jog and run. Did you use the same system for walk forward and backward and strafe left and right? So did you do for example, this is like this, right? Walk forward and backward and left and right. Did you do the in between of these and then blend all together?
We only authored them for the 4 cardinal directions. And how Tam mentioned that the system was kind of opt-in. For the forward direction, since that's the one that you would see most often, we had the most samples. And for the backward, left, and right, we had less.
And to achieve the angled movement, we would actually take those 4 cardinal directions and we would pivot them in the game. So we were never blending between forward and right in order to achieve 35 or 45 degree direction of motion. We would just pivot things, and then when you cross the threshold, we'd switch over to the next animation.
I think most departments have managers and leads and producers as well. It's the same across the board.
The only distinction is the engineering team. The engineering team doesn't have any pure managers. Everybody that's a lead in the engineering team is also currently working in functional engineer. That's the only exception. We also had producers. Oh, did we repeat the question? The question there was, what was the structure of the other teams in comparison to the structure we showed for the animation teams?
Thanks.
You have another one. What was the budget for the in-game animations?
You mean in terms of memory?
No, the budget. Oh, memory. I'm sorry,
Money.
memory budget.
Money. I actually don't know that number.
I don't know that either. I think it was a rolling budget.
It always rolled upward. Oh, and we had a question, what was the memory budget? The memory budget was between...
like 20 megs. Or something.
I think the threshold was 20 megs.
For everything.
For everything. We heavily multi-threaded some of the decompression and accumulation of animations. So if you laid it all out next to each other, probably be about 6 milliseconds, but it didn't actually cost that much at runtime because some of the animation work would happen alongside the physics.
The graph lookup was the most expensive.
Yeah. One of the things that was actually the most expensive, despite all the IK and blending and everything we're doing, ended up being, when we profiled it, the graph lookup, just finding the animations you wanted to play in any context. So when I talk about how we're developing that system for procedurally analyzing the animations and stitching them together, along with that comes a much cleaner way of determining what the next animation is going to play, finding it instead of looking it up through this big hierarchy that we had originally.
It seems like you have a lot of systems put in place to help the animators keep downtime to a minimum. Is that kind of pretty standard, the amount of stuff that you do for them on all projects, or even treat it all?
So the question was, we had a lot of systems, processes, and technologies in place to make animator downtime kept to a minimum, and whether that is standard across all projects or in the industry. It's standard across all projects for us. I think that actually goes across all teams too. Like even the environment guys, we try to make them work smoothly. Across all companies, I can't say that's true because I've worked at companies where there were no producers at all, and that was really tough. And I worked at companies where there were producers, but they weren't as good as ours. So the question was, we talked about the team structure with the engineer and the lead animator and the technical designer, but we didn't talk about who does the rigging. We have a special department that does that. We call them Myatech. They're tech artists. They do all the rigging, and they also provide tools for the animators.
And they're incredible.
Yeah, crazy good.
Okay, it looks like we're out of time, so one more question. Let's talk about that after we finish up. All right, I think that's it. Thank you all for coming.